YAML. ShrunkCovariance. Description. This class implements a shrunk version of the sample covariance matrix. Shrinking the covariance matrix means moving eigenvalues towards each other. This helps to reduce the variance of the estimated covariance matrix and, in turn, the variance of the estimated precision matrix. This estimator is particularly useful when dealing with high-dimensional data, where the sample covariance matrix may be poorly conditioned or even singular. Parameters. Name shrinkage. Type float. Description. Coefficient in the convex combination used for shrinking. Shrinkage 0 corresponds to no shrinkage, the sample covariance. Shrinkage 1 corresponds to complete shrinkage, all eigenvalues are equal. Default 0.1. Name assume centered. Type bool. Description. If true, data will not be centered before computation. Useful to work with data whose mean is significantly equal to 0 but is not exactly 0. If false, data will be centered before computation. Default false. Attributes. Name shrinkage. Description coefficient in the convex combination used for shrinking. Name location. Description estimated location, i.e. the center of the data. Name covariance. Description. Estimated covariance matrix. Covariance is a shrunk version of the sample covariance matrix. Computed using the formula. ShrunkCovariance 1 shrinkage sample covariance shrinkage diagsample variance. Name precision. Description. Estimated precision matrix inverse covariance matrix. Computed using the formula. Precision invariance. Methods. Name fit. Description computes the shrunk covariance matrix from the given data. Parameters. Name X. Type array like. Description training data, where n samples is the number of samples and n features is the number of features. Name score. Description computes the log likelihood of the data under the estimated Gaussian model. Parameters. Name X. Type array like. Description test data, where n samples is the number of samples and n features is the number of features. Name predict. Description predict the probability of a given data point under the estimated Gaussian model. Parameters. Name X. Type array like. Description test data, where n samples is the number of samples and n features is the number of features. Name sample covariance. Description returns the sample covariance matrix of the training data. Challenges. Name high-dimensional data. Description. The shrunk covariance estimator is particularly useful when dealing with high-dimensional data, where the sample covariance matrix may be poorly conditioned or even singular. Shrinking helps to regularize the covariance matrix and prevent overfitting. Fixes. Use shrunk covariance with a suitable shrinkage coefficient to regularize the covariance matrix and improve its stability. Name choosing shrinkage coefficient. Description. The optimal shrinkage coefficient depends on the specific dataset and application. Too much shrinkage can lead to underfitting, while too little shrinkage can lead to overfitting. Fixes. Experiment with different values of shrinkage to find the best balance between regularization and model accuracy. Use cross-validation to evaluate the performance of different shrinkage values. Name computational efficiency. Description. The shrunk covariance estimator can be computationally expensive for large datasets. The computational complexity of the estimator is on features 3, where n features is the number of features. Fixes. Consider using a more efficient implementation of the shrunk covariance estimator, such as the Leduit-Wolf estimator, which uses a faster algorithm for computing the shrinkage coefficient. If the dataset is very large, consider using a dimensionality reduction technique. such as Principal Component Analysis (PCA), to reduce the number of features before using the shrunk covariance estimator.